In this video, we want to take a look at some examples of evaluating improper integrals of type 2. In this example, we want to evaluate the integral from 0 to 3 of 1 over the square root of 3 minus x dx. Notice that our function in the integrand is not defined when x is equal to 3, and so this is going to be an improper integral of type 2, where the issue lies at our upper limit of integration. And so in order to deal with that particular undefined issue, we're going to rewrite our integral, the integral from 0 to 3 of 1 over square root of 3 minus x dx, as the definite integral from 0 to some value c of our function, 1 over square root of 3 minus x. And then we want to take the limit of this as c approaches 3 from the left, since we want to pick a value of c that is between 0 and 3. So to evaluate this limit of this integral, we want to compute the integral first. And in order to do that, we might want to rewrite the integrand as 3 minus x to the negative 1/2 power. And this will allow us to use the power rule to evaluate that antiderivative. However, we do have to be a little careful here because inside our composition, we have 3 minus x, not 3 plus x. And so here, if we make a really short u substitution, u equals 3 minus x, du will then be negative dx. And since we only have a dx, this tells us we have to adjust this by a factor of -1. So we can rewrite this as the limit as c approaches 3 from the left, the integral from 0 to c of negative, which we can pull outside of our integral, u to the negative 1/2 power du. We can then anti-differentiate this in terms of u. So we have the limit as c goes to 3 from the left of negative u to the positive 1/2 divided by 1/2, which is the same as multiplying by 2, and then evaluated from 0 to c. Now we need to be very careful here because these 0 and c are actually x values, so we cannot just simply substitute them in for u here. We need to first go back to the variable x. And so we want the limit as c goes to 3 from the left of -2, 3 minus x to the 1/2 power. And now we can evaluate this expression at c and 0 and subtract, and then evaluate our limit. So carrying on from this point, we want to continue to keep the limit as c goes to 3 from the left here. When we let x equal to c, we're going to get -2 times the square root of 3 minus c. Recall that we can rewrite something to the 1/2 power as the square root of that expression. So we get -2 times the square root of 3 minus c, minus -2 times the square root of 3 minus 0, which will be just the square root of 3. And so we can clean this up a little bit. Notice that we can make this second term a positive 2 square root 3. And as we take the limit as c goes to 3, the square root of 3 minus c gets closer and closer to 0. And so when we evaluate this limit, we get 0 plus a constant value of 2 square root 3. And so our integral that we wanted to compute from the beginning, the integral from 0 to 3 of 1 over the square root of 3 minus x dx, is equal to the constant 2 square root 3. And so this is an example of an improper integral that converges to the value 2 square root 3. In this example, we want to evaluate the improper integral from 0 to 2 of x natural log x dx. Notice that our integrand here, x times the natural log of x, is undefined at our lower limit of integration, which is 0. And so here we're going to rewrite our integral 0 to 2 of x natural log x dx as the integral from c to 2 of our integrand, x natural log x dx. And then we want to drag that c value towards 0 from the right, because we want to pick c bigger than 0 so that it lies in that interval 0 to 2. And so we want the limit as c goes to 0 from the right of the integral from c to 2 of x natural log x dx. Now, to evaluate this definite integral, we can hopefully recognize this as kind of a standard case of an example that requires integration by parts. And so here we can let u equal the natural log of x, and dv equals x dx. From this, we can know that du will be the derivative of the natural log of x, which is 1 over x dx, and v will be an antiderivative of x, which will be x squared over 2. And so we can substitute these values into our integral, and we have the limit as c goes to 0 from the right of 1/2 x squared natural log x evaluated from c to 2 minus the integral from c to 2 of x squared over 2 times 1 over x dx. And of course, this integral can be easily rewritten to be 1/2 integral c to 2 of just x dx by simplification. And so now we have our expression here that we can compute and then eventually take the limit as c goes to 0 from the right. So to continue on with this calculation, we're going to have the limit as c goes to 0 from the right of 1/2 x squared natural log x evaluated from c to 2 minus 1/2 times an antiderivative of x is x squared over 2, so that will give us an x squared over 4 evaluated from c to 2. And so we want to evaluate this expression in parentheses and then take our limit as c goes to 0. And when we do this, we get some constants and some expressions involving c. So on our first term here, we have 1/2 times 2 squared, which is just 2 natural log of 2, so 2 natural log 2, minus 1/2 times c squared natural log of c. And in our second term, we're going to subtract the quantity 2 squared over 4, which is just 1, minus the term c squared over 4. And so now we have 4 terms here. Notice that 2 of them are constant, the 2 natural log 2 and the 1. And so the limits of those will just be those constants. For the other terms, we have c squared over 4, and as c gets closer and closer to 0, c squared will get closer to 0, and so will c squared over 4. So that term will become 0. And 1/2 c squared natural log of c, we can also see will we get closer and closer to 0, although there we do need to use L'Hopital's rule or some other limit technique to justify this, but it is pretty easily shown that that limit will end up being 0. And then this tells us that our final value for our integral is going to be 2 natural log 2 minus 1. If you'd like to try a similar example, albeit one that's significantly simpler than the previous one, pause the video and evaluate the integral from 0 to 3 of 1 over x dx. Resume the video in a few seconds to see the full solution. So here, because the discontinuity is at our lower limit of integration at 0, we want to rewrite this as the limit as c goes to 0 from the right of the integrals c to 3 of 1 over x dx. We can evaluate this integral by taking an antiderivative of 1 over x, which is the natural log of x, evaluating from c to 3. And so we get the expression natural log 3 minus the natural log c. We want to take the limit as c goes to 0 from the right here. And of course, natural log 3 is a constant. And the function natural log of c ends up going to negative infinity. We can see that by quickly considering the graph of the natural log function, which looks something like this. And as we get closer and closer to 0 from the right, this function is getting smaller and smaller and smaller in the negative direction, and therefore that limit is equal to negative infinity. And so here, when we take the limit, we have a constant of natural log 3 minus negative infinity, and that gives us a positive infinity value here for our integral, and that means that this particular improper interval diverges. We don't have a particular number that it is equal to. It's equal to an infinite value. So this integral from 0 to 3 of 1 over x dx diverges.